Okay, first let's solve your quiz question about pure substances. Then we can have more question about closed system chapter. Okay, in the first row 1, we have the pressure and temperature. So we can use table A5 or table A4. You are free to use any one of them. I will use table A5. Okay, the pressure table. At pressure 200 kilopascal, and then I want to compare my temperature to the saturation temperature. Okay, so at table A5 at 200 kilopascal here, I want to compare the saturation temperature with my temperature. My temperature is 100 degrees Celsius. It is less than the saturation temperature. So it is a compressed liquid state. Okay, so T is less than Tsat. 100 degrees Celsius is less than 120.21 degrees Celsius. So it is a compressed liquid state. Okay, that is the requirement number 3 here. Okay, in order to find internal energy and enthalpy, we said it is compressed liquid, and in the previous tutorial we said that the compressed liquid is strongly dependent on the temperature more than the pressure. So in order to find the property, the specific internal energy and the enthalpy, I have to use the temperature table, not the pressure table, okay? And I will approximate the compressed liquid to be a saturated liquid. So I will go to table A4, not table A5, because the compressed liquid or water is strongly dependent on the temperature more than the pressure. So table A4, okay, and U will equal to UF, and H will equal to HF. So let's go to table A4 at 100 degrees Celsius. Okay, table A4. 100 degrees Celsius, and I will take the values for UF and HF to be my values for the specific internal energy and enthalpy. Okay, so U is equal to UF at 100 degrees Celsius, and it is equal to 419.06 kilojoule per kilogram. That is the requirement number 1. And for requirement number 2, H is equal to HF at 100 degrees Celsius also. And this will equal 419.06.17. Okay, for enthalpy, 17. Okay, kilojoule per kilogram. Now we finished row number 1. Let's go to row number 2. Also, I have the pressure, so I will use table A5, and I have information, the phase description, it is saturated vapor, okay? So I will use for specific internal energy UG, okay? U will equal UG, and my temperature will be the saturation temperature, because the saturation temperature is the temperature for saturated vapor, saturated mixture, saturated liquid. It is the temperature for any state inside the dome. Okay, so here we have saturated vapor, this state. So my temperature, if I draw the TV diagram, okay, so this temperature is the saturation temperature. Okay, so I will go to table A5. Okay, let's use another color, row 2. Row 2, I have the pressure, B is equal to 400 kilopascal, and it is saturated vapor. Okay, so I have the pressure. I will use table A5. I will go to table A5 at 400 kilopascal. Now my temperature is the saturation temperature. Okay, so T is equal to Tsat. T is equal to Tsat, and is equal to 143.61 degrees Celsius. And he says saturated vapor. Okay, so for U will equal to UG. That is the requirement number 4. And for U will equal to UG at 400 kilopascal. Okay, from table A5. So UG, this value 2553.1 kilojoule per kilogram. Okay, 2553.1 kilojoule per kilogram. Okay, we finished row number 2. Okay, let's go to row number 3. I have the temperature, so I will use table A4. Okay, table A4. I'm given the specific internal energy. So I will go to table A4 and compare my specific internal energy at temperature 250 degrees Celsius. I want to compare it. If it is higher than UG, then it will be superheated. If it is between UF and UG, it will be a saturated mixture. Let's see. Okay. So for row number 3, I will go to table A4 because I am given the temperature. So I will go to the temperature table. T is equal to 250 degrees Celsius. Okay. And I want to compare my U to UF and UG. Okay. The U value is equal to 1,500 kilojoule per kilogram. So let's go to table A4. Okay. 250 degrees Celsius. And compare my U. U is less than UG. Okay. My U is 1,500. Okay. And it is higher than UF. So it is a saturated mixture state. Okay. So if I wrote UF is less than U and it is U is less than UG, so it will be equal 1080.7 is less than my value for U 1500 and it is less than UG 2601.8. Okay, so it is a saturated mixture state. Okay, that is still it is not asked for the saturated mixture. Okay, we need to find the quality, okay, and the enthalpy, state 7 and state 6. Of course, when you never know that it is a saturated mixture, of course you need to find the quality. In order to find any other property in the like enthalpy or if it's the specific volume or the internal energy if it wasn't given, okay, you need to find the quality whenever you have a saturated mixture. Okay, so we'll start with requirement number 7 before 6. Okay, so for requirement number 7, X is equal to U minus UF over UG minus UF. Okay, that is UF and this one is UG, and already have U 1500, so it will be equal to 1500 minus 1080.7 over UG 2601.8 minus 1080.7. Okay, so X will equal to 0.276. Now, in order to find the enthalpy, okay, I will use this equation. H is equal to HF plus X HFG. HFG is the same like HG minus HF, okay? And we already have column for HFG in the table, okay? Of course, this one under the temperature, okay? Under the temperature 250 degrees Celsius. Okay, so I will go to the temperature 250 degrees Celsius and I will find HF, this value, okay, and also HFG, this value. Okay, so H will equal to 1085.7. X, we already calculated X in part number 7. It is 0.276 times HFG 1715.3. And this will equal to 1559.12 kilojoule per kilogram. Okay. So we finished row number 3. Let's go to row number 4. In row number 4, I have the pressure. Okay, so I will use table A5. So for row number 4, I will use table A5 because I have the pressure. Okay, the pressure is equal to 1000 kilopascal. And I'm given also the enthalpy. And I need to find the temperature and internal energy and the phase description. Okay, in order to find the internal energy, temperature, and the phase description, I have to compare my enthalpy, okay, to UG and UF, okay, and find if it is superheated, if it is saturated mixture, or it is compressed liquid. Let's see, okay. So I will go to table A5, okay, at 1000 kilopascal. So table A5, 1000 kilopascal, and I want to compare my enthalpy. The value for my enthalpy is 3588, okay. It is higher than UG, HG. HG is 2777. Okay, so H is higher than HG. That means that it is a superheated state. Okay, so 3588.85 is higher than HG, which is 2777.1. So it is a superheated state. Okay. So I will go to table A6 because it is the table for the superheated. Okay, so I will go to table A6, the superheated table state, table for the superheated. The pressure in the superheated table is in megapascal. I have the pressure in 1000 kilopascal. In order to convert from 1000 kilopascal to megapascal, I have to divide by 1000, so it will be equal to 1 megapascal. Okay, so I will go to table A6 under 1 megapascal for the pressure. Okay. And now I have different values for enthalpies. Okay, I want to know where is my enthalpy. My enthalpy is 3588.85. Okay, so it is a number. It is between these two numbers. Okay, of course you will not guess, or it is not clear that these two numbers, if you add them and divide by 2, it will give you my enthalpy. So my enthalpy is exactly in between. Okay, but usually in the exam you will not see this one, and it is not clear yani, because there is decimals. Okay, so you will do interpolation. Okay, but if you take these two values, H is equal to 3479.1 plus 3698.6. Okay, these two values, and you divide by 2, it will give you your enthalpy, 3588.85. And this means that I can also do the same thing for T, and the same thing for U. Okay, I will take these two numbers, 500 and 600, okay, and divide by 2. It will give 550, and the same thing for U. Okay, of course, in the exam or in the quiz, you cannot see this one. It is not clear. So what we will do is interpolation. Okay, so let's do the interpolation. I will do the table. I'll write the table T, U, and H. Okay. For H, we said these two numbers, 3479.1 and 3698.6. And my enthalpy was 3588.85. Okay. The corresponding values for the temperature are 500. And I want to find T that correspond to H given in the question, and 600. The same thing with U. Okay, I will take these two numbers, okay, and write them. So it will be 3125, and I want to calculate U, and the last number is 3297.5. Okay, then you will do interpolation. Okay, of course you will take T with H, and then you will take U with H, because in H you have the 3 values, and in U and T you have only 2 values, and one value is missing. Okay, so T minus 500 over 600 minus 500, it is equal to U minus 3125 over 3297.5 minus 3125, and this will give you that. Let's write also H. Okay, 3588.85 minus 3479.1 over 3698.6 minus 3479.1. We said in the previous lecture that we take the middle one minus the upper one and put it in the numerator. Then we take the the one in the one down 600 minus the upper value, so and put it in the denominator, and we'll do the same for others. Okay, now I will take in the calculator, I will write t with this values for h, and then I will and find t. Then I will take u and put it with h in the calculator and find u. Okay, so t will equal to 550 degrees Celsius. That is the requirement number 8. And for requirement number 9, U is equal to 3,211.25 kilojoule per kilogram. Okay. Of course, the requirement number 10 was the superheated state. Okay, it was superheated. So we finished the quiz question. So let's go to the questions about the closed system. But first, do you have any question in mind about the quiz? How many minutes it may take to solve this quiz? I think 15 minutes. I solved it in 15 minutes. So let's, if you don't have any question, can you please solve with us today's quiz? I don't know what is the quiz for your quiz today, okay? I don't have it. Maybe in next tutorial, inshallah. Okay, so if you don't have question regarding this problem, let's go to chapter 4, the question about chapter 4. Okay, so here we have air. Okay, so we have air. It is contained in a variable load piston cylinder. We have a piston cylinder, okay, device equipped with a paddle wheel. So we have a shaft work here on the system, on the air, okay. Initially, air is at 400 kilopascal and 17 degrees Celsius, okay. Usually when you find the temperature is high and the pressure is low compared to the critical pressure and the critical temperature, okay, if you search for it, then we will assume that air is ideal gas. Usually in most of the question, we will say that the air is ideal gas, okay, in order to use the ideal gas equations, okay. That is the first thing, okay. The paddle wheel is now turned by an external electric motor. Okay, so there is a motor that turns this paddle wheel, and then there will be a shaft work until 75 kilojoule per kilogram of work has been transferred to air. Okay, so I have for W shaft. Okay, and it is kilojoule per kilogram, so it is small w, it is per kilogram, it is specific, okay? So it will equal to 75 kilojoule per kilogram, okay? And of course, I have the pressure given it is equal to 400 kilopascal. And the temperature, it is 17 degrees Celsius. And if it is in Kelvin, you will add 273, it will be 290 Kelvin, okay? During this process, heat is transferred to maintain a constant air temperature. Okay, so the temperature is constant. So this temperature is, if this one is T1, then it is equal to T2, and in general it is equal to T. It is constant. Okay, so we have isothermal process. Okay, when the temperature is constant, we call it isothermal process. Okay. While allowing the gas volume to triple. So initially we have a volume for the gas, okay, it is V1. Then this volume is tripled, so V2 is equal to 3 times V1, okay? The ratio between V2 over V1 is equal to 3, okay? He asked calculate the required amount of heat transfer in kilojoule per kilogram. So we have heat transfer added, okay? Heat transferred, heat is transferred to maintain a constant air temperature. So we added heat transfer, okay, to maintain a constant heat temperature, because if you add the heat, you will maintain the temperature, okay. So he asked for the Qn, and Qn, he asked for kilojoule per kilogram. So he asked for the small Qn, okay. So in order to calculate Qn, usually in closed system like piston cylinder device or rigid tank, we'll use the energy balance. Okay. Now I am dealing everything in specific per kilogram. So I will use this form of energy balance. It is En minus E out. Small energy, يعني kilojoule per kilogram, is equal to delta E system. Okay. En in general, it contains Qn small plus Wn small. Okay. And E out contains Q out small minus also W out. Okay. Usually we wrote this form like Q minus W, okay, equal to delta E system. In general, يعني in kilojoule, okay. And we assume that Qn is positive and W out is positive, okay. And this sign, this minus sign, is already in the equation, okay. And Q out is negative, and Wn is in negative, okay. When you add Qn, it is positive, so like this one. Wn, it is in negative. I will add it here, and there is negative in the equation. It will give me positive Wn. Then minus Q out, okay, it is in minus, okay. Then I will put it like it is. It is minus, okay, in E out. And for work out, it is positive, okay. It is positive, and there is minus in the equation. It will be negative here. So instead of thinking about the signs and it is positive, it is negative, okay, I will write the general form. This one is the general form, Qn plus Wn. Okay, anything n, heat transfer or work, minus Q out minus W out, anything heat transfer out or work out. And it is equal to delta E system. Okay. So we will ignore, I will not look at the signs. I will write them, all of them like this. And if I have Qn or Wn, I will put them. If I don't have Qn, I will remove it. And depending on the question, okay? Now, in this question, I have Qn. He said, I want to calculate Qn. So I have Qn in the question, okay? I have also Wn because there is work shaft on the air, okay? So I have Wn for the shaft, okay? I don't have Q out, so Q out is 0, okay? Do I have W out? Whenever you see a piston cylinder device, okay, there is something called boundary work, okay? Boundary work, okay? We call it WB. You have the piston cylinder device, okay? Something like this, okay? This piston moves up and down. It may become here, okay, or down. And when you solve a thermodynamics question, you will take air. Here we take air as my control volume. This is my system, right? When I move up, okay, when I move up, what will happen? That my control volume will increase, okay? This boundary under the piston will move up, okay? And if I do compression process, okay, this boundary will move down, okay? And my control volume will decrease. So I have a moving boundary. This boundary moves with the piston, okay? So this boundary work, we represent it as a change in volume, okay? Its general equation is equal to the integration of P dV, okay? So the integration from state 1 to 2, okay, because you moved from the initial state to the final state of B dV, okay? Based on the question, maybe the question is isothermal, like this question, maybe you have constant pressure, you will deal with this equation, okay? And we will see the different cases, okay? So if you have expansion process means that the piston moves up, okay, and the volume increased, okay. The piston initially was here, okay. Then it was in the second state here. This one is 1, this one is 2. Then the boundary, we call it boundary work out, okay, and we will put it instead of the work out in the question, okay. And if you have compression process, okay, so this one was your first state for the piston, and then you move down, okay, so you compress the air inside the cylinder, okay, so you have work boundary N, okay. Here in this question, what happened? That he said that the volume is tripled, right? Okay. when the volume is tripled, means that my control volume increase, it expands, it go up. Okay, if it go up, so I have boundary work out. Okay, so instead of W out, I will put minus boundary work out. Okay, whenever you see piston cylinder, of course you will have a boundary work. Rigid tank, for rigid tank, you will not have boundary work because rigid tank is not moving. We saw it in the previous tutorial. It is not moving. The volume is constant. Okay, and if the volume is constant, then there will be no change in the volume, and this will equal to 0. Okay. But here we have piston cylinder device. So in general, the remaining for this equation is Qn plus the work shaft minus W work out, the boundary work. Okay, and it's equal to delta E system. Delta E system consists of 3 things. Okay, it consists delta E system consists of the kinetic energy, the change in kinetic energy, the change in potential energy, and the change in the internal energy. The usual case in most of the question, you will have a stationary system. The piston is not moving. The rigid tank is not moving. You don't have elevation. He didn't mention anything about velocity, okay? Because this one is the kinetic energy is equal to half mv squared, okay? And the potential energy is equal to mg h, okay? If you don't have elevation h or z, or you don't have velocity, he said stationary system, then this one will cancel, equal to 0. This one will cancel, it is equal to 0. The remaining is delta U, okay? The internal energy. So here in this question, he didn't give me elevation, okay? He didn't give me velocity. He didn't say anything about kinetic or potential energy. So I will assume it is stationary system. They are equal to 0, and the remaining is delta U, okay? So now I have Qn, that is the required for me to find in the question. I have the work shaft into the system. Okay, it moves the pedal. Okay, the motor moves the shaft and then it moves the pedal wheel. Okay, and I have a boundary work out because the volume increased. It is tripled. Okay, so I have expansion process, and expansion process is a process that means it is work done by the system on the surrounding. So it is out, okay? So WB out. But compressed, it is work done on the system. So it is WBN, okay? Now in this question, you have tripled volume, or the volume is tripled. Then we have work boundary out. So that is the final form for this question, okay? And with every question, you will do the same thing. You want to see what you have, and what the boundary work, is it out, it is expansion process, or it is in, it is compression process. I have Q out, I have WN, is the system is stationary, so now then I will put delta U. So that is the usual way, okay? So I will arrange the equation, okay, in order to calculate Qn. So Qn is equal to delta U plus W boundary work out, okay, minus W shaft, okay? He said in the question, it is that the temperature is constant, right? It is isothermal process, okay? If the temperature is constant, means that delta U is equal to 0. Why? Because delta U, you have equation related to the specific heat, the specific heat CV at constant pressure, at constant volume. CV, delta U is equal to CV delta T, okay? And delta T is 0 because T1 minus T2 minus T1 is equal to 0, okay? They are equal to each other. We have isothermal. So delta U is equal to 0. So I will cancel delta U from my equation. So the remaining is Qn is equal to the boundary work out minus the work of the shaft. Okay. Now I have the isothermal process. Okay. So in order to find the W work out, or the boundary work, I have this equation for the boundary work. Okay. The boundary work is equal to the integration from 1 to 2 B dV. Okay. The pressure, we said in the beginning that we will assume that air is ideal gas, right? In order to use the ideal gas law. So the ideal gas law, BV is equal to MRT, okay, for V capital, for M meter cubed. So this mass is constant, okay? It is a fixed system. This chapter called closed system, the mass is fixed. So M is constant. R You can find it from table A2A, okay? A1 0.287 or from table A2A 0.827 are the gas constant for air. So it is also a fixed number, a constant, okay? And the temperature also a constant. He said in the question it is isothermal, okay? T is equal to 119 Kelvin, okay? You must use Kelvin. So this right side is constant. So it is equal to C, a constant number, okay? So B is equal to C over V. Okay, so I can replace B in the integral by C over V. So the boundary work, okay, and this boundary work is in it is capital. It is in kilojoule. Okay, and now I'm dealing in kilojoule, and I will see how I can go to small w. Okay, because my question is in kilojoule per kilogram. Okay, so this one will equal to C over V from 1 to 2 dV. C is constant, so I will take it out from the integral, okay? Then I will have dV over V. This is equal to C ln V2 minus ln V1, okay? And from the property of the ln, it will be equal to C boundary. The boundary work is equal to C ln V2 over V1, and this will equal to MRT ln V2 over V1, okay? Because C is equal to MRT. At the beginning, we said that C is equal to MRT. And in the question, I need to put my boundary work in kilojoule per kilogram. This one is the capital W. So I have to divide by the mass. Okay, I will divide by the mass. I'll divide by the mass. Then I will have the small boundary work, and it is out in this question. Okay, equal to RT ln V2 over V1. And V2 over V1, we said it is 3 because the volume is tripled, right? Okay. So it will equal to RT ln of 3. R is 0.287, okay? R is equal to 0.287 kilojoule per kilogram Kelvin, okay? And T, you have to put it in Kelvin also. It is equal to 290 Kelvin. Then I will substitute in the equation in order to find the boundary work out. Okay, so it is equal to 0.287 times the temperature, 290, ln of 3, and this will give you 91.4 kilojoule per kilogram. Now I found the boundary work out, and I already given in the question the work of the shaft. It is the 75 kilojoule per kilogram. Then now I can calculate Qn. So the boundary work out 91.4 minus the work shaft is 75. And this will give you 16.4 kilojoule per kilogram. That is required from us in this question, the Qn. If you have any question regarding this problem, you are free to ask if you have any question. Okay, let's go to the next question. Okay, in this question we have a mass, okay, M is equal to 15 kilogram of air, and we said خلاص air is like ideal gas. Okay, in a piston cylinder device is heated from 25 to 77 degrees Celsius. Okay, so I have T1 is equal to 25 degrees Celsius, and T2 is equal to 77 degrees Celsius. Okay, by passing a current through a resistance, so a current is passing here, okay, through a resistant heater inside the cylinder. So there is a work in from the resistant heater on the air, okay? So I have Wn, okay, which is the electric work, We, okay? The pressure inside the cylinder is held constant. So my pressure B1 is equal to B2. In general, it is equal to B, and it is constant, and it is equal to 300 kilopascal, okay? During this process, okay? and a heat loss of 60 kilojoule per kilogram. So I have heat loss, so it is Q out. Okay, so Q out, I have Q out, and it is capital Q because it is in kilojoule, so it is equal to 60 kilojoule. Determine the electric energy supplied in kilowatt per hour. Okay, the electric energy supplied, he means WE. Okay, WE. I want to find WE and this work in kilowatt. The conversion factor between kilowatt and kilojoule is that 1 kilowatt hour. 1 kilowatt hour is equal to 3,600 kilojoule. So usually we find our answer in kilojoule. Okay, what we will do is that we will divide by 3,600 in order to get it in kilowatt per kilowatt hour. Okay. Okay. Now let's write my energy balance for closed system. Okay. And this time I have in kilojoule only, not in kilojoule per kilogram. So I will write the capital letter. So En minus E out. It is equal to delta E system. Okay. Do I have any kinetic energy change, any potential energy change? Do I have any elevation velocities? No. So this means that the potential energy change and the kinetic energy change is 0, and my system is stationary. So I only have delta U. Okay. And for this part, I have, for En, I have WEN, right? The work in by the electric heater. Okay. Do I have any QN? Nothing mentioned about QN. We have Q out. Okay. So I finished En. Let's go to minus E out. Okay. I have Q out, right? So minus Q out. Do I have any work out? Okay. I am looking for both heat transfer and work. Okay. We said whenever you see a piston cylinder, then you will have boundary work. Okay. You will have boundary work. Now, is a boundary work is in or out? Okay, you have to know if it is in or out. Maybe I will put it here before the WEN in the EN. Maybe it is work out. So in order to find, we know that we assume that air is ideal gas, right? Okay, and we have equation for the ideal gas that P1 V1 over T1 is equal to B2 V2 over T2, right? B1 is equal to B2. He said held constant. The pressure inside the cylinder is held constant. So I can cancel B1 and B2 because it is equal to each other. Okay. And I can arrange this equation to be T2 over T1 is equal to V2 over V1. So over V1. So this one is a direct relation. Okay. Relation between the temperature and the volume. If I increase the temperature, means I increase the volume. Okay. Of course, in this question, I increase the temperature from 25 to 77 degrees Celsius. Means that I increase V1 also to V2. So the volume is increasing. Means this system will come here. Okay, this piston will come here, and then my control volume will be this one. Okay, means that the volume increased, and I have expansion process inside the piston cylinder device, and that means that my boundary work is out also. Okay. So I have boundary work out. Okay. So I will put it also in the E out. So it will be minus boundary work out. Okay. So I finished writing the closed system energy balance equation. Let's find the boundary work out. Okay. We say that that is the general equation from 1 to 2 V dV. Now the pressure is constant, right? All what I will do, that I will take the pressure out, and then I will integrate dV. It will give me delta V. It is equal to B V2 minus V1. This one V is capital. Okay, this one in meter cubed. Okay. Usually we don't deal with this one in kilojoule. We must multiply by the mass. Okay, usually that's what will happen, and we're already given the mass in the question. So we know that from the previous chapters that V is equal, capital V is equal to M times the specific volume, small v. So I will replace V2 by M V2 and V1 by M V1, V small one. Okay, so this one will equal to that the boundary work out, okay, in kilojoule is equal to MB small v2 minus small v1. Okay, that is the boundary work. Okay, I have the pressure, I have the mass, and I need to find the specific volumes. But let's see what will happen. Let's see how we will get out of the specific volumes. Okay. Now that is my equation. I will replace W work out by by this equation MB V2 minus V1. So I will have that WAN minus Q out minus MB small v2 minus v1 is equal to delta U is equal also M small u2 minus u1. Okay, so it is equal to M u2 minus u1. Help. Now I will move this one to the another side. Okay, to the other side. So WEN minus Q out will equal to M u2 minus u1 plus M B v2 minus v1. I can take the mass as a common factor from the right side. And if you remember that the enthalpy is equal to U plus BV, B small, BV small, okay? So that's what I will do, okay? I will arrange the equation. I will take M as a common factor, okay? And I will say that U2 plus BV2 minus, and I will open a small bracket, U1 plus B1 V1. This term is equal to H2 minus H1, okay? And I will have the enthalpies instead of the specific internal energy, and PV is the pressure and the specific volume, okay? This will equal to WEN minus Q out, okay? I'm given the question Q out, so I have Q out. I have the mass. The remaining that I don't have H2 and H1. I don't have H2 and H1 in order to calculate WEN, okay? So if I put WEN in one side, it will equal to Q out plus M H2 minus H1, okay? Q out is given. In order to calculate M H2 minus H1, as we did for in the previous question, we substitute here delta U by CV delta T, and it was delta T is equal to 0, so delta U is equal to 0, okay? Here also, delta H, small delta H, is equal to CB, specific heat under constant pressure, times delta T. I have delta T, and specific heat, it is we call it the average specific heat because we take it if you have two temperatures, we will take the specific heat under these two temperatures. In the question, he gave me two temperatures, 25 and 77, state at state 1 and at state 2. So I have the temperature, so I have delta T, and I can find the specific heat at T average between T1 plus T2 over 2, okay, at table A to B. Okay, if you go to table A to B, this table, okay, you will have different values for CB and CV for different gases. Okay, if you don't have any of these 6 gases, then you will use table A 2A under 300 Kelvin, and you will just take this numbers CB, CV, or K. But here we have two temperatures, and I have air as my gas in the question. Okay, so I will use these two the T average, which is equal to my temperatures are 25 plus 77, okay, over 2. And this will give you 51 degrees Celsius. And as you can see, this table is in Kelvin. So I have to convert in Kelvin. So 51 in Kelvin is equal to, if I add 273, it will is equal to 324 324 Kelvin. You will not find 324, but you can approximate 324 to be 325 approximately, okay, in order to take the corresponding values for 300 and 350 Kelvin temperatures and divide by 2. So I will take these two numbers for 1.005 for the CB and 1.008, add them and divide by 2, okay, in order to get CB. So CB average is equal to 1.008, the CB at temperature 350, and plus 1.0015 over 2, okay? And this will give you 1.0065 kilojoule per kilogram Kelvin. So that is my CB. Now I have CB. Okay, instead of MH2 plus minus H1, I will put CB average T2 minus T1, and I have Q out given in the question. Now I can find WEN required from me in the question. Okay, so WEN is equal to Q out is 60 given in the question. CB we said it is equal to 1.0065. Okay, times 77 minus 25, and this will give you that WEN in kilojoule is equal to 845 kilojoule. He asked in the question to be the unit in kilowatt hour. So I will divide by 3,600. Okay, and this will give you 0.235 kilowatt hour. And by this we finish this question. If you have any question about this problem, you can ask. Okay. So let's move to the next question. I don't know if we can finish this question or no. So we have a piston cylinder device initially contains steam. So we have steam. So I know that I will use table A4 to A6. Okay. In the previous question, we have air. So we use the ideal gas law. When you have steam, A4 to A6. When you have refrigerant, you will use A11 to A13. Okay. At pressure, B is equal to 200 kilopascal. Okay. And temperature 200 degrees Celsius with a volume V is equal to 0.4 meter cubed. Initially, so let's say it is P1, T1, V1. Okay. At this state, a linear spring. So we have a linear spring, this one. So a linear spring means it has a direct relation with the distance. When you increase the value for the compression or the extension for the spring, then you have a direct relation with the force. If you increase this one will increase also. Okay, it's touching the piston but exerts no force on it. So it is only touching the piston. It is not pushing or moving the piston anywhere. Okay, heat is now slowly transferred to the steam. So we have Qn to the system. Okay, we have Qn to the system, causing the pressure and the volume to rise. So we have B2 equal to 250 kilopascal. Okay, and volume V2 is equal to 0.6 meter cubed. Show the process on a PV diagram. So I need to show the process on a PV diagram. Okay, with respect to the saturation lines, and determine at part A the final temperature, T2, because it is the final temperature. Okay, and the work done by the steam, he said work done by. Okay, so it is the boundary work out, because we said the boundary work by the steam or by the working fluid, by the thing that inside the cylinder, means it is expansion process. So it is work out. Okay, when you never see work done by, then it is work out. Done on the system, it is work in. So he is asking for the boundary work, okay, out from the system. Okay, and see the total heat transferred. Okay, so Qn. So in part C, I need to find Qn. Okay. So now, in order to draw the PV, the process on a PV diagram, okay, I have to know the state 1 and state 2. Is it superheated? Is it saturated mixture? Where is the region for these states? Okay. So I will use for state 1 the pressure table. I have the pressure, I have the temperature, I can use any one of them. I will use the pressure table, table A5, okay? And I want to compare my temperature to the saturation temperature at the quiz question, okay? So I will go to table A5 at 200 kilopascal and compare my temperature. My temperature is 200, okay? So it is higher than the saturation temperature, so it is a superheated state, okay? So T1 is higher than Tsat, okay? So 200 is higher than 121.20.21. So it is superheated state, okay? So I know that this state 1 is superheated state. So if I draw that at 200 kilopascal, so this one, this axis in kilopascal, so this one is 200 and this one specific volume, so it is meter cubed per kilogram. Okay, at 200 kilopascal, this point, I have a constant temperature line corresponding to this one, which is a Tsat, okay, the 120.21 degrees Celsius, okay? My temperature is higher than this constant temperature line, so it is above this line, it is something here, okay, for example. Okay, so this one is T1, it is equal to, for example, 200 degrees Celsius, okay? And it must pass also with the point with 200 kilopascal, okay? So it is something here at this point. It corresponds also to the pressure 200 and to the and it is located on the constant temperature line for 200 degrees Celsius, okay? That is my state. It is superheated state. So that is the place for state 1, okay? Now, in order to find state 2, okay, I have here the pressure and the volume, but in the tables I don't have columns for volume or tables that contains volume. I have for specific volume, right? I have for small v. So I have to, in order to calculate the state, the phase description of the state, I have to convert V to V small, okay, V capital to V small. We know that V capital and V small are related with the mass. So V small T is equal to V capital T over the mass, okay? I have V2 capital, but I don't have the mass. Okay, so in order to find the mass, I can do the same thing with the first state because I already have its point. I have more information. I have the temperature here, but here I don't have the temperature. So I can get here also the specific volume from state 1. Then I can use this equation that mass is equal to V1, given the question this value, okay, over the specific volume from the table. Then I can get the mass from state 1, okay. Then I will substitute it in state 2 in order to get the specific volume V2, and then I will compare V2 with VG and VF in order to know the phase description. Then I will draw it in the PV diagram, okay. Now let's find V1, okay. I have, we said it is superheated state, right? State 1. So I will use table A6. Okay. Under pressure, the pressure in table A6 is in megapascal, and my pressure is 200 kilopascal. I will divide by 1000. Okay. So it is equal to 0.2 megapascal. So I will write that my pressure P1 is equal to 0.2 megapascal. And under temperature, T1 is equal to 200 degrees Celsius. I want to find V1, and it is equal to, from the table, if you go to table A6, at 0.2 megapascal, right? 0.2 megapascal. 0.2 megapascal here and 200 degrees Celsius. So the specific volume V1 is equal to this value. So V1 is equal to 1.08049 meter cubed per kilogram. Okay. Now I have found V1. I will find the mass. So M is equal to V1 0.4 meter cubed or V1 small 1.08049. and this will give us that the mass is equal to 0.3702 kilogram. And then I will put it here in order to find the specific volume V2. So V2 is equal to the capital V2 0.6 meter cubed over the mass 0.3702. And this will give you 1.6207 meter cubed per kilogram. I will take this value, okay, and go under the pressure 250 kilopascal, table A5, okay, and compare my V2 with VG and VF, okay. So I will go to table A5 at 250 kilopascal here, okay, and compare my volume, my specific volume with VG and VF. As you can see, VG is 0.71873. My volume, specific volume, is 1.6207. So it is higher than the saturated vapor specific volume. So it is also a superheated state. So V2 small is higher than VG. 1.6207 is higher than 0.71873. And this means that it is superheated state, okay? So I will use table A6 in order to find the temperature, what is required from me in this question at part A, because now I have B2 and I have also V small 2. I can use it from table A6 in order to find T2, okay? So for B2 is equal to 250 kilopascal, and we know that table A6 is in megapascal, so it is 0.25 by dividing by 1000, okay? Megapascal, okay, and V2 is equal to small V2 is 1.6207 meter cubed per kilogram. So I have to find my temperature, okay? So I will go to table A6. If you can see here, 0.25 megapascal is between 0.2 and 0.3. So we don't have a table or a column for the pressure 0.25 megapascal. Whenever you face this problem, you need to do maybe double or triple interpolation, okay? How we do double interpolation? You will search for your specific volume value under this pressure, 0.2, okay? And you will find that it is equal to V2 is 1.6207. It is between these two numbers, okay? Between these two numbers. And you will do interpolation between these two numbers and the temperature 400 and 500. And you will go again for 0.3 megapascal under this specific volume. And you'll see that your volume 1.62 is between these two values here, and you will do interpolation between V and the temperature 700 and 800, and then you will get an answer for the temperature from the pressure 0.2 megapascal and an answer for the temperature from the 0.3 megapascal. You will take these two answers and divide by 2 because the pressure is exactly between 0.2 megapascal and 0.3 megapascal, my pressure. Then my temperature also is between the answer from 0.2 megapascal and 0.3 megapascal. So it is a long story, and I don't think it will come in the exam, but to have an idea, I think that tutorial is finished, and if you have any question, you can ask. You are most welcome. خلاص, if you don't have any question, السلام عليكم. Thank you very much. We will see you inshallah in the next tutorial.